Once upon a time, I had a dream of an algorithm. An algorithm so elegant and graceful, where bubbles rose from the depths of the oceans. It is a sorting algorithm that brings balance to, well, everything. I decided I would build this algorithm. Here is what I discovered. Firstly, I noticed that the blue elements received the bubbles. I decided to create a loop, iterating from the end of the array to the second element. I will not include the first index, because it already has its bubble. Next, I realized that we can loop through all the elements before the bubble receiver. Then we can compare them with the value after. If the value after is bigger, simply swap them. That is it. We have built the algorithm. Now it is time for an analysis. I'll leave that up to Dr. Royal Meadow, the greatest algorithms genius in existence. She is the epitome of algorithmic vitality.
Now let's calculate the number of comparisons. We perform one single comparison inside the inner loop. We iterate through the inner loop. We start at iteration 1. We end at iteration I-1. This results in this summation where we add one comparison for each iteration from j equals 1 to j equals I-1. We then iterate through the outer loop. We add the number of comparisons in the inner loop for each outer loop. The inner loop iterates through all the elements before I, so it runs I-1 times. If we plug in I, we see it results in 2-1, iterated up by 1, all the way up to n-1. This results in n-1 times n divided by 2. We know this because of the famous Gauss's trick. If you are unfamiliar with the trick, check out my video in the description. Carl Gauss discovered the trick as a young boy. Let's consider how many swaps are in the bubble sort algorithm. First, let's find the number of swaps in the best case. The best case is that the array is already sorted. Remember, we make swaps when a value is bigger than the value to its right. This will never happen if the array is sorted, which means there will be 0 swaps in the best case. Now, let's consider the worst case. This means the array is in reverse order. Notice the first value bubbles to the top, and the reverse order array shifts to the left by 1. Notice it happens again, and for every iteration of the outer loop. This means we will have one swap for every iteration of the inner loop. We perform one single swap inside the inner loop. We iterate through the inner loop. We start at iteration 1. We end at iteration I-1. This results in this summation where we add one swap for each iteration from j equals 1 to j equals I-1. We then iterate through the outer loop. We add the number of swaps in the inner loop for each iteration of the outer loop. The inner loop iterates through all the elements before I, so it runs I-1 times. If we plug in I, we see it results in 2-1, iterated up by 1, all the way up to n-1. This results in n-1 times n divided by 2 swaps. We know this because of the famous Gauss's trick. If you are unfamiliar with the trick, check out my video in the description. Now let's consider the average case. We would expect half of the inner loop iterations to have a swap. Let's demonstrate this with a random variable where x is the number of swaps in an inner loop. 1 represents a swap. 0 represents no swap taking place. The probability of these values for x are 0.5 for both. This means our expected value is 0.5. If you are unfamiliar with random variables or expected value, please check out the videos in the description. We end up with this summation. It is the same as before, except we expect half of a swap per inner loop iteration. Let's pull out the constant. If you are unfamiliar with this summation property for constants, check out the video in the description for summation properties. We've already solved this summation. We get 1/2 times the result of the summation.
Pas de soleil, pas de soleil, pas de soleil, pas de soleil.